I want to quickly mention QLCS tornadoes because, section 1 here is like we hate them. No one likes them. They embarrass you. They cause people to fuss. But they happen. I think there's lots of definitions. One thing is not call it a gustnado like you see called on some media outlets. They're not gustnados. QLCS tornadoes are part of the thunderstorm. So it's something with a connection that's being vented through the thunderstorm cell itself, where a gustnado is just out on the gust front by itself, something lower end. EF or QLCS tornadoes can reach EF3 in intensity. We've had EF2 tornadoes in the Tulsa forecast area that have been QLCS tornadoes. They can be EF3, so they're not necessarily brief. They're not necessarily weak. They can be pretty significant. I tell our office, don't shadow box with them, don't guess at them, don't light up the whole line. But if you think you've got one and you think you understand what's going on, certainly put out a tornado warning for it. The 0 to 3 kilometer shear is very important in understanding that. You can anticipate this some. We've noticed that if the 0 to 3 kilometer shear is more than 30 knots and it starts to be, especially if it's perpendicular, but if it starts to be something more than 45 degrees in an angle to the line of the storms, it's getting more important. The QLCS thing that spun up in Louisiana yesterday, if you all were watching the radar, the 0 to 3 kilometer shear was starting to go past 45 degrees. So it wasn't truly at 90, but it was starting to go past 45. And right when that happened, that's when that strong QLCS spun up, and that's when the TDS flared up from that one tornado that was in the line. You can anticipate this some. These aren't just totally mysterious things that just suddenly go, oh my gosh, what happened? The 0 to 3 kilometer shear in that configuration holds the gust front back. And so it keeps the gust front underneath the updraft. And that's what you want. You want that vortex sheet to spin up where it can be vented by the cell itself, and not just something that's rolling out on the gusty winds out ahead of it. So these actually can be anticipated. You can get acceptable at this. Now, you'll never catch the warning. By the time you see it, it will already be doing damage. I mean, it's a process that happens basically at or near the surface. By the time you can recognize it, you've already missed it. But then you go on, do I go ahead and continue the warning because there could be another one? Those become really tough decisions at some point. This is a storm. You can see the QLCS storm to the east of Fort Smith, and you can see it's got the little reflectivity hook. We call it elephant trunk in the office because it's sort of, especially when it really wraps up, kind of looks like an elephant trunk. The circulation is here. The ground survey from this event is this. We did our normal ground survey. We tried to mark the vectors of which way things fell. Then I scanned the map and went back and just put pencil to paper and tried to draw out streamlines with it. But you can see a confluent pattern right there. You can see where there's convergence, and it's a narrow enough convergence, and the damage was significant. It was a decent EF1 tornado, and so we could pick out damage that looked like tornado damage underneath the couplet, underneath the little hook. So we do know that at times those are real tornadoes. Sometimes I think QLCS circulations are bigger than we think. I think this one's a really cool one. This is going over Broken Arrow. And the TDWR there is in north side of Broken Arrow. But I just want to call your attention to the hydrometeors being pulled in up here. These little showers are passing in front of the squall line. As this one got up here, and as this QLCS circulation intensified, notice how it stripped some of the raindrops off and pulled it back in here. If you actually went from the bottom of down here where it looks like that's where the southern extent of the influence of the QLCS is, and come up here, we're talking many miles. It's not a tiny little mesocyclone thing that's all quick spin up and whatever. They actually can dominate the circulation within many miles of them. I think they all come. There's a continuum of them, just like anything else. I think there's some that border more looking like supercell circulations. There's some that look more just like gust fronty things. But the bottom line is you don't often know what they're going to be. And I think there are times that they're more important than we think. The last couple things here. Scale matters. Just on the big Cape days, the mesocyclones often begin to organize higher than you think. This time of year, 4,000 feet, maybe you're looking at stuff. And stuff higher than that, you're like, it's too high, whatever. But as we get into the bigger Cape days, we get into the latter part of spring, sometimes those mesocyclones don't really begin to show themselves until they're higher up. And sometimes that's easy to dismiss and say, I've got increasing mesocyclone organization at 10,000 feet. Like, well, okay, nobody lives at 10,000 feet. Well, in the high Cape days, it all works because it's like comparing that's me and Ed Calnisi, the WCM from the Tulsa office, next to some ginormous basketball player. If you were just going to do a knee examination on the basketball player and just measure the distance from the floor up to his knee and then took that same measurement to me, you'd be looking at a different part of my body. So it's the same thing with the storms. If the storm is now 70,000 or 60,000 feet tall or whatever it is, you got to expect it to be scaled differently than a storm that was 30,000 feet. So where these circulations show up in the vertical, it matters, and it matters to the depth of the storm. So I just point this out real quick on hail, since not everything is all tornadoes, and of course that's mostly what we talked about. But I noticed that if the 0 to 6 kilometer shear is less than 15 knots, the hail probably doesn't make it to the ground, or at least it underperforms what you think it should be at the radar. I like reflectivity of the minus 20, knowing the shear, and knowing if there's a mesocyclone in there. If you can give me those three things, I can guess hail size to some degree. And actually, that's the shear pushing everything out. I just stole this from the spotter training talk, but just to give you the idea that the shear is everything on the hail. The hail may still form up there, but if it has to come back down through the warm up draft, it's going to underperform. Hail will overperform with the mesocyclones, and so if you're trying to guess hail sizes, I like this Kavanaugh and Schultz study. I thought was a pretty good one, especially since it validated the numbers that I liked, and you always drift towards the studies that validate the numbers you liked. I like 60 dBz to the minus 20 as the beginning of a severe thunderstorm warning, plus or minus those other factors. If the shear is less than 15 knots, then better not. If there's a mesocyclone in it, better go quicker than that. But I think this is a good study. A lot of cases in the Southern Plains that they sorted through and did several things with them. Just real quick on downbursts, you guys all know all this stuff, but from the standpoint is that when a downburst happens, the highest velocities are going to be in the lowest 300 or 400 feet, stuff you're not going to see on the radar at any distance away from the radar. So don't expect to see in a summertime July downburst case and I only sampled 30, 35 knots. Well, the peak wind was actually down at 400 or 500 feet where you couldn't get a good look at it. The only thing you might have a shot at is the mid-altitude radial convergence aloft, where as the downdraft comes down, you get convergence maybe at 8, 9, 10,000 feet as air funnels into the downdraft and then spreads back out. I've seen that before, but you better be fast because that's on the orders of minutes before the wind hits the ground. Again, it's not going to typically give you a lot of lead time, but at least it helps you understand the reports you might be getting. Land spout stuff, the mesonet might be the best warning tool you have for a land spout because it's not mesocyclone driven. It's on a boundary. You've got opposing wind flow. If we start getting reports of a tornado that I suspect is a land spout, first thing I do is run to the mesonet. And if I got a boundary that shows me southeast winds up against northwest winds, something opposing each other, I'm gonna lean towards the idea that hey, there's probably something there. And 3 calls in 90 seconds is a bad thing because everybody's starting to call it in. But basically, do you have an updraft on a local shear that could be stretched? And the best way of knowing that is to go look at the surface data and try to figure that out. This is the last stuff. Just to know what you're warning for and then warn or not. The worst thing in the world is to not have some idea of what is important to you and to sit down there and try to be flexible. Kind of know in your mind, this is what I'm going to warn for, and then do it. And you'll be right 90% of the time. And those times that you're not right, adjust and learn from that. But if you know what it is, you'll be well served, and you'll be consistent, and you'll be scientific, and you'll have nothing to be ashamed of. Instead of you're just suddenly playing whack-a-mole now with the radar. Like no one feels good after that because you don't know really why you were making the decisions that you did. And I've talked to you about this before. Noisy cockpits are good. Asking for input. You don't always know everything that there is to know about the storms, and probably the biggest thing on there, the hardest thing to do is not warn. If you've got a mesocyclone approaching Oklahoma City and it's kind of marginal and everything's kind of marginal, the easiest thing in the world to do is issue a tornado warning, let all the stomach acid drain back out. You're good now if you're covered, hey, and if you didn't get it, well, the weather's kind of hard to forecast, it's kind of unpredictable, this is inexact science, you can go through all that routine. The hardest thing to be a truly good warning forecaster is to sit there and go, not yet, I don't think so, I don't think it's quite right yet. And you look at that, and you really have to balance that from better safe than sorry. You can always get the argument that, well, better safe than sorry. And that better safe than sorry is exactly right on any given day. But if it was good on Monday, is it just as good on Tuesday, Wednesday, Thursday, and Friday? After you added up your last 10 better safes than sorries, and you've issued warnings very liberally, then you're in the stake of like, okay, maybe I need to reassess some. So it's just really a tough balance. It's great that you guys have a chance to work with the folks here that are actually operational in the actual warning and forecast world. And this is a great class, and I always appreciate Dr. Cohen for allowing me to come down and say hi to you guys for a little bit.